Hello there, and welcome to Midnight Science. I'm so glad you found your way here tonight. Maybe you've been wondering about the roads not taken, the choices unmade, or the infinite possibilities that shimmer just beyond the edge of what we know. Tonight, we're going to explore something vast and mysterious, something that exists at the boundary between physics and philosophy, between mathematics and dreams. Tonight, we're drifting through parallel universes. There's nothing you need to do now. Just let yourself settle. Let the day fall away like leaves from a tree. Tonight, we'll move gently from one cosmic possibility to another, exploring the many worlds interpretation, quantum branches, and the strange mathematics that suggests reality might be far larger than a single universe. Some of what you hear may stretch your mind. Other ideas might simply float by like clouds, interesting, beautiful, and strangely comforting. If these quiet explorations help you rest, feel free to like and subscribe. It helps others find their way here too. But for now, just breathe. Let your thoughts soften. And let's begin this slow journey through the infinite. The multiverse may contain every possible version of you. Right now, in this moment, you're reading these words, but according to some interpretations of quantum mechanics, there are countless other versions of you making different choices. In one universe, you decided not to listen tonight. In another, you fell asleep 5 minutes ago. In yet another, you never discovered this channel at all. The many worlds interpretation, proposed by physicist Hugh Everett in 1957, suggests that every quantum event splits reality into multiple branches. Each possible outcome actually occurs, just in different universes. It's not that these universes are far away in space. They're separated by something else entirely, by the branching structure of reality itself. This means that somewhere, in the vast landscape of possibility, there's a version of you who made every choice differently, who took that job, who didn't take that trip, who said yes instead of no, not as ghosts or dreams, but as real physical beings living out alternative timelines. It's a strange thought, both humbling and oddly comforting. Every path exists somewhere. Every version of your story is being told. Quantum mechanics suggests reality splits at every decision point. The splitting doesn't happen because of human choices alone. It happens constantly at the quantum level, trillions upon trillions of times per second. Every time a particle could go left or right, every time an atom could decay or remain stable, every time a photon could be absorbed or reflected, reality branches. These aren't dramatic cosmic ruptures. They're quiet, invisible divisions woven into the fabric of existence. Most happen far below the threshold of human perception. In the microscopic realm where particles exist in superposition, in multiple states at once, until something forces them to choose. But in the many worlds view, they never really choose. Instead, all possibilities occur. The universe simply splits to accommodate every outcome. You experience one branch, one thread in an ever-expanding tapestry, but the other branches are just as real, just as physical, unfolding in parallel to your own. Right now, as you listen, countless versions of this moment are playing out. Infinite variations, infinite yous, all experiencing slightly or dramatically different realities. Some physicists believe parallel universes are mathematically inevitable. The idea of parallel universes isn't just speculation or science fiction. For many physicists, It's a natural consequence of the mathematics that describes our world. The equations of quantum mechanics, when taken seriously, seem to demand multiple worlds. The wave function, the mathematical object that describes quantum systems, contains all possible outcomes simultaneously. In the traditional interpretation, observation causes this wave function to collapse into a single result. But collapse is mysterious, arbitrary, and hard to define. What counts as an observation? Where does the randomness come from? The many worlds interpretation eliminates this problem entirely. There's no collapse. The wave function never reduces to a single outcome. Instead, it continues to evolve smoothly, deterministically, branching into multiple realities. Each branch experiences a different result, but all branches are equally real. It's a solution that trades one kind of strangeness for another. Instead of mysterious collapse, we get infinite splitting. But mathematically, it's elegant, even beautiful. Reality becomes a vast tree, branching endlessly, every possible history unfolding somewhere in the structure. The many worlds interpretation was once considered radical. When Hugh Everett first proposed his interpretation in the 1950s, it was met with skepticism, even dismissal. The idea that reality splits into countless parallel universes seemed absurd, extravagant, impossible to test. For years, it remained on the margins of physics, a curious idea that few took seriously. But over time, attitudes shifted. As physicists grappled with the deep strangeness of quantum mechanics, the many worlds interpretation began to seem less radical and more inevitable. It solved problems that other interpretations struggled with. It was simpler in some ways, requiring fewer assumptions, no special role for observers, no mysterious collapse. Today, while still debated, it's considered a legitimate, even mainstream interpretation. Surveys suggest that a significant portion of quantum physicists find it plausible, perhaps even probable. What once seemed like wild speculation is now taught in universities, discussed in textbooks, and taken seriously by some of the brightest minds in science. Sometimes the most radical ideas are simply the ones we haven't gotten used to yet. Parallel universes might be layered like pages in a book. Imagine reality as a book with infinite pages. Each page is a complete universe, a full three-dimensional space filled with galaxies, stars, and perhaps life. Our universe is one page. Right next to it, separated by the thinnest margin, is another universe, then another, stacked infinitely in a direction we cannot see or point to. This is the idea behind certain models of the multiverse, particularly those involving extra dimensions. In string theory and related frameworks, our universe might be a three-dimensional brain floating in a higher dimensional space. Other brains, other universes, could exist nearby, separated by microscopic distances in dimensions we don't experience. These parallel universes wouldn't be quantum branches. They'd be entirely separate spacetimes, perhaps with different physical laws, different particles, different fundamental constants. We can't see them or visit them, but they might be right next to us, layered like invisible pages, each telling its own story. It's a vision of reality that's vast beyond imagining, and yet strangely intimate. Another entire universe, just a fraction of a millimeter away in a direction you'll never turn. Every choice you didn't make is playing out somewhere else. Think of a moment when you made a difficult choice. Maybe you moved to a new city or stayed where you were. Maybe you reached out to someone, or let the moment pass. Maybe you took a risk, or played it safe. In the many worlds view, both choices happened. When you stood at that crossroads, reality split. One version of you went left, another went right, and both are equally real. This isn't about regret or what-ifs in the usual sense. It's about the structure of existence itself. If quantum mechanics is correct, and if the many worlds interpretation is the right way to understand it, then every possibility is actualized somewhere. The path you didn't take isn't hypothetical. It's real, unfolding in a parallel branch of reality. You'll never meet the other versions of yourself. You'll never know what they experienced. But in a sense, they're out there, living lives that diverged from yours at countless quantum junctures, writing different stories in the vast library of existence. Some universes might have different physical constants. In our universe, certain numbers define how reality works. The strength of gravity, the mass of an electron, the speed of light. These constants are finely tuned, balanced in a way that allows stars to form, atoms to bond, and life to emerge. But there's no obvious reason why these numbers have to be what they are. In a broader multiverse, especially one arising from eternal inflation or string theory, different regions of space might have different constants. In some universes, gravity might be stronger, collapsing everything into black holes before stars can form. In others, it might be weaker, leaving matter too diffuse to clump together. Most of these universes would be sterile, hostile to complexity, incapable of supporting anything like life. We exist in one of the rare universes where the constants happen to fall within the narrow range that permits structure, chemistry, and consciousness. This is sometimes called the anthropic principle. We observe a life-friendly universe not because the universe was designed for us, but because we could only exist in a universe with the right properties. In the vast multiverse, countless barren universes exist. We simply couldn't be in one of them to notice. Inflation theory suggests the multiverse is eternally creating new universes. Shortly after the Big Bang, our universe underwent a brief period of exponential expansion called cosmic inflation. In a fraction of a second, space grew by an enormous factor, smoothing out irregularities and setting the stage for everything that followed. But in some models, inflation never truly ends. While it stopped in our region of space, allowing our universe to cool and form galaxies, it continues elsewhere. In distant regions, far beyond what we can ever observe, space is still inflating, bubbling off new universe pockets like foam. Each bubble is a universe unto itself, causally disconnected from the others. Inside each bubble, inflation stops, a Big Bang occurs, and matter and energy begin their long evolution. But outside, in the inflating space between bubbles, the process continues forever. This is eternal inflation, a scenario in which the multiverse is not just vast, but infinite and eternally creative. New universes are being born all the time, each with potentially different properties, each its own island in an endless cosmic sea. Our universe is just one bubble in an infinite foam, one story among countless others. The laws of physics might be different in other universes. In our universe, light moves at a certain speed. Matter attracts through gravity. Particles have specific masses and charges. These aren't just arbitrary rules. They're the deep structure of reality, encoded in the equations that govern everything. But in a truly vast multiverse, especially one involving string theory's landscape of possible vacuum states, the laws themselves might vary. One universe might have electromagnetism, but no strong nuclear force. Another might have extra dimensions that aren't compactified, leading to radically different physics. In some universes, atoms might not be stable. In others, there might be no light at all, or time might flow differently, or cause and effect might not operate in familiar ways. Most of these universes would be unrecognizable, governed by physics so alien that nothing like stars, planets, or life could exist. We inhabit a universe with a specific set of rules, one that happens to support complexity in consciousness. But out in the multiverse, if it exists, the variety might be endless. Every possible way for a universe to be realized somewhere in the infinite expanse. Quantum entanglement might connect parallel worlds. Quantum entanglement is one of the strangest phenomena in physics. When two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein famously called it spooky action at a distance. In the many worlds interpretation, entanglement takes on a new meaning. When you measure an entangled particle, reality splits. In one branch, you measure spin up, in another, spin down, and in each branch, the distant entangled particle shows the corresponding result. But here's the strange part. The two particles aren't communicating across space. They're connected through the branching structure of reality itself. The correlation exists not because of a signal, but because of how the quantum state evolves across multiple worlds. Some physicists have even speculated that entanglement might create subtle connections between parallel universes, not bridges we could cross, but mathematical links in the underlying structure. It's a hint that the multiverse, if it exists, might not be a collection of isolated bubbles, but a deeply interconnected web. You might be living in a simulation inside another universe. What if our entire universe, with all its galaxies, stars, and complexity, is actually a simulation running on some advanced computer in another, higher-level reality? This isn't just science fiction. It's a serious philosophical and scientific hypothesis. The argument goes like this. If it's possible to create detailed simulations of universes, and if civilizations eventually develop that capability, then there would be many more simulated universes than real ones. Statistically, we'd be more likely to inhabit a simulation than base reality. In this scenario, our universe would be one layer in a potentially infinite stack of simulations within simulations. Each level might have slightly different laws, programmed by the simulators above. And those simulators might themselves be living in a simulation, created by beings in an even higher reality. It's dizzying to contemplate, but it's another form of parallel universe. Not quantum branches or distant bubbles, but nested realities, each containing the next. Like Russian dolls made of information and code. We might never know if we're simulated, but the possibility adds another layer of strangeness to an already mysterious cosmos. Some universes might exist in completely different dimensions. We experience 3 dimensions of space and 1 of time. But mathematics allows for universes with different dimensionality. String theory, for instance, suggests that reality might have 10 or 11 dimensions, most of which are curled up too small to see. But what if some universes have more dimensions that are large and accessible, or fewer, A two-dimensional universe would be a flat plane, impossibly thin, where beings could only move forward, backward, left, and right, never up or down. Such universes would have radically different physics. Gravity behaves differently in different dimensions. Atoms might not be stable. Light might not propagate. Most alternate dimensional universes would be inhospitable to any form of life we could recognize. But in the vast landscape of possibility, they might exist. Universes with 4 spatial dimensions, or 5, or 12. Universes where time has multiple dimensions, or none at all. Realities so alien that we can barely imagine them. Governed by mathematics that diverges from our own in fundamental ways. Our 3 dimensions feel natural because they're all we've ever known. But they might just be one possibility among many. The universe might split every time you observe something. In the many worlds, interpretation, observation isn't special. It's just another physical interaction. But that interaction has profound consequences. It entangles you with the system you're observing. Before you look at a quantum particle, it exists in superposition, in multiple states at once. When you observe it, your brain state becomes entangled with those different possibilities. In one branch of reality, you see outcome A, and your brain records that memory. In another branch, you see outcome B, and that version of you remembers differently. From your perspective, the universe seems to pick one result. But from a God's eye view, the universe split. Both versions of you exist in different branches, each convinced they experienced a single definite outcome. This happens constantly. Every time light hits your retina, every time a neuron fires, every time any quantum event affects your body, new branches form. You're not moving through a single timeline, but sprouting countless versions of yourself, each diverging into their own future. It's happening right now as you read. Trillions of times per second, a silent, invisible branching, creating a vast tree of realities, all rooted in this moment. Parallel universes might explain quantum weirdness. Quantum mechanics is deeply strange. Particles exist in multiple places at once. Measurements seem to affect the past. Distant objects correlate in ways that seem impossible. For a century, physicists have struggled to make sense of it. The many worlds interpretation offers an explanation. What seems weird in a single universe makes sense in a multiverse. Particles aren't really in multiple places at once. They're in different places in different branches. Measurements don't collapse possibilities into one result. They split the observer into multiple versions, each seeing a different outcome. The strangeness doesn't disappear, but it shifts. Instead of mysterious quantum jumps and spooky action, we have a reality that's constantly branching, creating vast webs of parallel worlds. It's still strange, but it's a different kind of strange, one that follows logically from the mathematics. Whether this is the right interpretation is still debated, but it's a reminder that the universe's deepest mysteries might have solutions we haven't imagined yet. Sometimes understanding doesn't mean making things less weird. It means finding a new framework where the weirdness makes sense. Some parallel universes might be older or younger than ours, in an eternally inflating multiverse. Different bubble universes don't all form at the same time. Some emerged billions of years before ours. Others are forming right now in distant regions of the inflating space. A universe that formed early would be older, its stars more evolved, its galaxies more mature, perhaps even its civilizations more advanced if life arose there. A newly formed universe might still be in its first moments, hot and dense, with no structure yet, just a sea of particles and energy. Time itself might flow differently in different universes, depending on their physical constants and expansion rates. What feels like 13.8 billion years to us might correspond to a very different duration elsewhere. This means the multiverse, if it exists, has a history, a timeline of cosmic births stretching back infinitely and forward forever. Our universe is somewhere in the middle of this vast temporal landscape, one moment in an eternal process of creation. We live in a specific age of our universe, but in the broader multiverse, all ages exist simultaneously, scattered across the infinite foam of space and time. There could be universes where time flows backward. Time, as we experience it, flows in one direction. The past is fixed. The future is open. Entropy increases. Memories form. Cause precedes effect. But is this direction fundamental, or just a feature of our particular universe? Some physicists have speculated that in other universes, or even in other regions of a very large universe, time might flow differently. In a universe with reverse thermodynamics, entropy might decrease rather than increase. Events would unfold from what we'd call future to past. Inhabitants of such a universe, if they could exist, would perceive their direction as forward and ours as backward. To them, their memories would feel normal, their cause and effect sensible. The asymmetry of time might not be a law of nature, but a local feature, an arrow that points one way in some places and another way elsewhere. It's a mind-bending thought. Somewhere, perhaps, a universe is running in reverse, where stars grow younger, where shattered glass spontaneously reassembles, where the natural flow is opposite to ours, and beings, if they exist, think of their direction as the only one that makes sense. Cosmic inflation might have created infinite copies of you. In an eternally inflating multiverse, space is infinite and constantly growing. Within that infinite space, matter arranges itself in every possible configuration. Given enough room and time, this leads to a strange conclusion. If space is truly infinite, then every possible arrangement of matter must repeat. Somewhere, incredibly far away, beyond the reach of light or observation, there's another galaxy just like the Milky Way, another solar system just like ours, another Earth with another version of you, living a life identical to yours up to this moment. In fact, there would be infinitely many such copies, scattered across the infinite expanse. Some are exact duplicates. Others differ in tiny ways, a single atom displaced, a single thought altered. The further you go, the more variation you'd find. But the exact copies are out there, living your life, reading these words, thinking these thoughts. It's not science fiction. It's a consequence of infinity and probability. In an infinite universe, even the most improbable arrangements occur, not just once, but infinitely many times. You are unique, but only locally. In the vast sweep of existence, you're repeated endlessly, a pattern that the universe writes again and again. The boundary between universes might be made of energy if parallel universes exist as separate bubbles in a higher dimensional space. What lies between them? Some models suggest that the boundaries between universe bubbles are not empty, but made of energy. Vast walls or membranes separating one cosmic domain from another. These boundaries might have their own physics, their own dynamics. In some scenarios, bubble universes can collide, their boundaries meeting and merging in cataclysmic events. Such a collision might leave traces, patterns in the cosmic microwave background, or anomalies in the large-scale structure of our universe. Astronomers have searched for signs of such collisions, looking for circular patterns or temperature variations that might indicate our universe once brushed against another. So far, no definitive evidence has been found, but the search continues. The boundaries might also be sites of unusual phenomena, regions where the laws of physics transition from one set to another, neither fully one universe nor the other. They'd be cosmic borderlands, liminal spaces where reality itself is in flux. If they exist, these boundaries are utterly beyond our reach, but they're a reminder that even the spaces between universes might be filled with wonder. You might be quantum entangled with versions of yourself. In the many worlds view, all the parallel versions of you share a common origin. You all started as the same person, the same quantum state, before countless branching events separated you into different worlds. This shared history creates a kind of connection, not a physical link you could use to communicate, but a deep structural relationship encoded in the mathematics. You and your parallel selves are different branches of the same quantum wave function, still part of a larger whole. Some physicists and philosophers have speculated about what this means for identity. Are you one person or many? If all your parallel selves are equally real, then in a sense, you're spread across the multiverse, experiencing every possible life simultaneously from different perspectives. It's a strange form of immortality. You might die in one branch, but continue in countless others. Every possible future you might have is playing out somewhere. The full story of you isn't contained in a single timeline, but in the vast branching tree of all your possible lives. You are singular and multiple, unique and endlessly repeated, one thread in a tapestry that's always expanding. Some physicists think parallel universes are untestable and therefore unscientific. Not everyone embraces the multiverse. One common criticism is that parallel universes, especially in the many worlds interpretation, might be impossible to test. If we can never observe other branches, never visit other bubble universes, never confirm their existence, then are they really science? Or just metaphysics dressed in equations? This is a serious objection. Science traditionally relies on testability, the ability to make predictions and check them against observation. If a theory predicts things we can never measure, some argue it crosses the line from science into philosophy. Defenders of the multiverse respond in several ways. First, the many worlds interpretation makes testable predictions about quantum mechanics, just like other interpretations. Second, even if other universes are unreachable, their existence might have indirect observable consequences. And third, the multiverse might simply be a consequence of theories we can test, like inflation or string theory. The debate continues, but it highlights a deep question. What counts as scientific knowledge? And how do we navigate ideas that seem to follow logically from our best theories, even when they stretch beyond what we can directly observe? The multiverse might be the ultimate solution to the fine-tuning problem. Our universe seems remarkably fine-tuned for life. Change the strength of gravity by a tiny fraction, and stars wouldn't form. Adjust the mass of the electron slightly, and chemistry wouldn't work. Alter the cosmological constant, and galaxies wouldn't coalesce. This fine-tuning has puzzled physicists for decades. Why are the constants of nature set so precisely? Some see design, others see coincidence. But the multiverse offers a different answer: selection bias. If there are countless universes with different constants, then of course we find ourselves in one where the constants permit life. We couldn't exist anywhere else to wonder about it. The vast majority of universes are sterile, lifeless, governed by physics hostile to complexity. But in the rare ones where the numbers align, life emerges, evolves, and eventually asks why. It's not that our universe is special, it's that we could only exist in a universe that appears special to us. The multiverse turns a profound mystery into a statistical inevitability. Whether this is truly an explanation, or just pushing the question back a step, remains debated. But it's a powerful idea, one that reframes the fine-tuning problem in a radically different light. Quantum computers might access information from parallel worlds. Quantum computers are strange devices that exploit quantum superposition and entanglement to perform calculations that classical computers struggle with. They work by manipulating qubits, quantum bits that can be in multiple states at once. Some researchers have speculated, provocatively, that quantum computers might be tapping into parallel universes. In the many worlds view, a quantum computer in superposition exists in multiple branches simultaneously. Each branch performs part of the computation. When the results are brought together through interference, it's as if the different worlds are collaborating. This is a controversial and mostly metaphorical idea. Quantum computation doesn't require multiple worlds to work, and other interpretations of quantum mechanics can explain it just fine. But the many worlds view offers an intriguing picture. Your quantum computer is sharing the workload with countless parallel versions of itself, all working together across the multiverse. Whether or not this is literally true, it captures something profound about quantum mechanics. The computational power comes from somewhere, from some vast space of possibilities that quantum systems can explore in ways classical systems cannot. The multiverse, if it exists, might not just be passive scenery. It might be an active resource, woven into the very fabric of computation and information. There might be a universe where you never existed in the vast branching tree of many worlds. Most branches contain some version of you, but trace back far enough, and there are branches where the events leading to your existence never occurred. Perhaps your parents never met. Perhaps they met but didn't have children. Perhaps a cosmic ray struck a different atom at a crucial moment of conception, and a different person was born instead. In the quantum lottery that led to your existence, countless unlikely events had to align just so. For every branch where you exist, there are likely far more where you don't. Timelines where your genetic pattern never assembled, where the particular configuration of atoms that makes you never came together. These universes aren't sad or wrong. They're simply different branches of the tree, paths the universe took that didn't include you. Other people exist there instead, living their own lives, making their own choices, unaware of the nearby branches where a different person, you, is living a different story. Your existence is contingent, improbable, and precious, not inevitable, but actual. You exist in this branch, and that's enough. Parallel universes might solve the measurement problem. The measurement problem is one of quantum mechanics' deepest puzzles. Before you measure a quantum system, it exists in a superposition of all possible states. But when you measure it, you always get a single, definite result. How does the superposition collapse into one outcome? What counts as a measurement? When exactly does it happen? The many worlds interpretation dissolves this problem entirely. There is no collapse. The superposition never reduces to a single outcome. Instead, the observer becomes entangled with the system, and both branch into multiple versions. In each branch, a different outcome is observed. From inside any given branch, it looks like collapse. You experience one result, randomness, unpredictability, but zoom out, and there's no randomness at all. All outcomes occur deterministically in different branches. This is why many worlds is appealing to some physicists. It removes the arbitrary, hard-to-define moment of collapse. It makes quantum mechanics fully deterministic and universal. The price is accepting that reality consists of countless parallel branches, most of which you'll never experience. It's a trade-off. Eliminate one mystery by embracing another. But for some, it's a trade worth making. Some universes might loop back on themselves in time. What if a universe could be a closed time-like curve, a space-time where time loops back on itself? In such a universe, moving forward in time could eventually bring you back to your starting point, not by traveling through space, but by the curvature of space-time itself. General relativity allows for such solutions, at least mathematically. They lead to strange paradoxes. Could you meet your younger self? Could you change the past? Most physicists suspect these solutions are unphysical, ruled out by unknown laws or consistency requirements. But in a vast multiverse, perhaps somewhere there's a universe where time truly loops. Causality would be radically different. Events might not have a clear beginning or end, just a circular flow. Inhabitants, if they could exist, might experience time differently, perhaps without a sense of past and future as we know them. These speculative universes push the boundaries of what we think is possible. They remind us that time, like space and matter, might be far stranger and more varied than our local experience suggests. There might be a universe where consciousness works differently. In our universe, consciousness seems to emerge from complex neural networks, from the firing of billions of neurons in brains made of flesh and chemistry. But is this the only way awareness can arise? In other universes, with different physical laws or different fundamental particles, consciousness might have entirely different substrates. Perhaps it emerges from quantum processes that are suppressed in our universe. Perhaps it arises from crystalline structures, from plasma dynamics, or from forms of organization we can't even imagine. There might be universes where consciousness is more fundamental than matter, where awareness isn't something that emerges from complexity, but something woven into the basic fabric of reality. Conversely, there might be universes where consciousness never arises at all, where matter organizes into intricate patterns but never becomes aware of itself. The nature of your awareness, the fact that there's something it's like to be you, might be contingent on the specific physics of this universe. In other cosmic neighborhoods, minds might work in ways utterly alien to us, experiencing reality through frameworks we couldn't begin to comprehend. Your consciousness is a mystery even here. In the multiverse, it might be one solution among countless others. The many worlds interpretation suggests reality is deterministic. It seems paradoxical, but the many worlds interpretation actually makes quantum mechanics completely deterministic. There's no randomness, no dice rolling, no mysterious moment when possibility becomes actuality. In the traditional view, quantum measurements are fundamentally random. You can calculate probabilities, but you can't predict which outcome will occur. This randomness seems built into the universe at the deepest level. But in many worlds, the wave function evolves smoothly and predictably, according to the Schrödinger equation. All outcomes occur. There's no random selection, just branching. From the perspective of the universal wave function, everything is determined. The apparent randomness we experience is an artifact of our perspective. We follow one branch, and from inside that branch, it feels like the universe chose randomly, but it didn't choose. It simply split into all possibilities. This means that if you could somehow see the entire many-world structure, you'd see a perfectly ordered, deterministic system. The randomness is subjective, a feature of living inside one branch while being unable to perceive the others. Free will, determinism, and chance take on new meanings in this framework. The universe is deterministic, but you still can't predict which branch you'll experience. It's determinism without predictability. Some parallel universes might be completely empty. Not every universe in the multiverse needs to be filled with matter and energy. Some might be vast, empty spaces where nothing ever formed. In the landscape of possible universes, there are configurations where the initial conditions or the physical constants prevent structure formation entirely. No density fluctuations to seed galaxies, no particles that can clump together. Perhaps even no particles at all, just empty space expanding forever. These universes would be profoundly lonely, voids stretching infinitely in all directions with nothing to observe them, nothing to evolve within them. No stars would ever shine, no atoms would ever bond, no thought would ever arise to wonder why. They'd be like dark rooms that no one ever enters, existing but never witnessed, real but never experienced. In the democracy of the multiverse, emptiness might be just as common as fullness, or perhaps even more so. Our universe, teeming with galaxies and complexity, might be a rare jewel in an ocean of cosmic emptiness. The fact that anything exists here at all, that patterns can form and persist, is a contingency, not a guarantee. Even nothingness might have infinite variations. Your decisions might create the most branches. While every quantum event causes branching, not all branches are equally significant. A particle decaying in deep space creates two branches, but they might be nearly identical except for that one microscopic difference. But when you make a complex decision, when your brain processes information and multiple outcomes hang in the balance, you might be creating branches that diverge in substantial ways. Your choice to speak or stay silent, to turn left or right, to say yes or no, these might generate branches that grow increasingly different over time. In a sense, conscious agents might be particularly powerful branching points. Every thought that passes through your mind might correlate with countless quantum events in your brain, each potentially creating new worlds. This doesn't mean you're literally creating new universes with your choices. The branching happens at the quantum level regardless. But your decisions might be where microscopic quantum differences amplify into macroscopic, meaningful divergences. You're not just living in the multiverse. You're actively participating in its structure, a branching point where quantum possibilities become lived experiences, where the abstract mathematics of superposition becomes the concrete reality of different lives. Every moment you exist, you're at the center of a cosmic flowering. There could be universes made entirely of antimatter. In our universe, matter dominates. There's far more matter than antimatter, an asymmetry that remains one of physics' great mysteries. But in other bubble universes, the balance might be different. Imagine a universe where antimatter won the early cosmic lottery. Galaxies made of anti-atoms, stars burning anti-hydrogen, planets formed from antimatter. From the inside, it would look and behave exactly like our universe. Antimatter follows the same laws, forms the same structures, creates the same chemistry. But if that universe ever touched ours, the contact point would explode with the total annihilation of matter and antimatter, converting mass entirely to energy. The boundaries between such universes would be catastrophic meeting points, walls of pure energy. These antimatter universes wouldn't be evil twins or mirror opposites in any meaningful sense. They'd simply have the opposite charge structure, a different solution to the same equations, equally valid, equally real. In the vast multiverse, symmetry might be restored not within universes but between them. For every matter-dominated cosmos like ours, perhaps there's an antimatter twin, balancing the cosmic ledger across the fuller reality. Parallel universes might explain where you go when you die. This is perhaps the most comforting and controversial implication of many worlds. If reality constantly branches, creating copies of you that diverge with every quantum event, then in some branches, the events that would lead to your death in this timeline simply don't occur. A car swerves slightly differently. A cell's mutation is prevented by a random quantum fluctuation. A photon strikes a molecule in your brain at just the right moment to change a neural firing that saves your life. In the many worlds view, there are always branches where you survive, where you keep going, where the story continues. You can't experience the branches where you die, by definition. So from your subjective perspective, you might always find yourself on a branch where you're still alive. This is called quantum immortality and is highly speculative, more philosophy than physics. Most physicists are skeptical, but it's a thought that emerges naturally from taking many worlds seriously. You might not be able to die from your own perspective, always finding yourself on increasingly improbable survival branches, living on forever across the multiverse's infinite tree. It's a beautiful idea. Whether it's true is another question entirely. The multiverse might be organized in a fractal pattern. Fractals are patterns that repeat at different scales. Self-similar structures that look the same whether you zoom in or out. Some cosmologists have speculated that the multiverse itself might be fractal. Imagine universes within universes, each level of organization containing smaller versions of the same structure. Our observable universe might be a tiny part of a much larger cosmic structure, which itself might be part of an even larger one, and so on infinitely. At the same time, Perhaps within the quantum foam of space-time at the smallest scales, entire miniature universes branch off, each containing their own galaxies and complexity, too small for us to observe but fully realized in their own right. This fractal structure would mean that scale is relative. What seems like the entire universe to beings at one level might be a single atom to beings at another. The boundaries between levels might be smooth, with no clear dividing line between micro and macro, just endless repetition of similar patterns. In a fractal multiverse, you could zoom in or out forever, finding new universes at every scale, each reflecting the structure of all the others. Reality becomes an infinite Russian doll, pattern within pattern, endlessly. Some physicists propose we live in the most average possible universe. The principle of mediocrity suggests that we shouldn't expect to find ourselves in a special or unusual situation. Applied to the multiverse, this would mean we should expect to live in a fairly typical universe, one that's common among all the possible options. If certain physical constants or cosmic conditions lead to more observers, more beings capable of wondering about their existence, then most observers would find themselves in universes with those properties. We'd expect to be typical, not exceptional. This principle can be used to make predictions. If our universe has a property that makes it unusual compared to other life-bearing universes, that might suggest we've misunderstood something. Conversely, if our constants are about what we'd expect given anthropic selection, that supports the multiverse hypothesis. Of course, average is hard to define when you're talking about infinite universes, but the basic idea is that you're probably not special on a cosmic scale. Your universe is likely one of countless similar ones, populated by beings asking the same questions. It's a humbling thought. Even in the infinite diversity of the multiverse, you might be remarkably ordinary, just one more observer in one more typical universe, wondering about all the others. Quantum branching might happen at the speed of light. How fast does reality split? When a quantum event occurs, when do the new branches form? The mathematics of quantum mechanics doesn't specify a speed for branching, and the many worlds interpretation inherits this ambiguity. Some physicists speculate that the branching propagates outward at the speed of light, the fastest that information can travel in our universe. When a particle decays here, the split might ripple outward in an expanding sphere, gradually entangling more and more of the universe with the different outcomes. This would mean that distant parts of the universe might not have split yet from your perspective, at least not relative to events happening near you right now. The branching is local before it becomes global, spreading through space-time like ripples on a pond. Of course, this is highly speculative. The notion of when branching happens might not even be well defined. From the universal wave function's perspective, there's no moment of splitting, just a continuous evolution of quantum superpositions. But it's intriguing to imagine that right now, as quantum events occur in your brain, branching waves are radiating outward at light speed, gradually dividing the universe into parallel copies, spreading your story across the multiverse. There might be universes where mathematics works differently. Mathematics seems universal, true independent of physical reality. 2 + 2 = 4 in every universe, right? But some philosophers and physicists have questioned whether mathematical truth is truly absolute, or whether it might vary across the multiverse. Perhaps in some universes, the logical axioms that underlie mathematics are different. Not that 2 + 2 = 5 in the sense of our arithmetic, but that the fundamental rules governing mathematical reasoning might be structured differently, leading to entirely different mathematical frameworks. These universes might be so alien that we couldn't even describe them. If the logic itself is different, if the basic principles of reasoning don't match ours, then their reality might be genuinely incomprehensible to us. More modestly, there might be universes where different mathematical structures are physically realized. In our universe, certain geometries and symmetries are embodied in particles and forces. In others, different mathematical objects might be fundamental, leading to radically different physics. Mathematics feels like the one unchanging truth, the bedrock beneath everything else. But in the fullest possible multiverse, even mathematics might be contingent. One language among many, describing one corner of reality, but not all of it. The foundations might go deeper than we can imagine. You might be simultaneously alive and dead in parallel worlds. Right now, in this branch of reality, you're alive, conscious, experiencing this moment. But if the many worlds interpretation is correct, there are branches where this isn't true. Branches where you've died, where the string of events that kept you alive in this timeline played out differently there. This is similar to Schrödinger's famous thought experiment with the cat, but applied to you. Just as the cat can be both alive and dead in superposition before the box is opened, you exist in a superposition of alive and dead across the many worlds, until we specify which branch we're asking about. But unlike Schrödinger's cat, this isn't just a thought experiment. If many worlds is correct, it's literally true. Across the multiverse, every possible fate has befallen you. You've died in countless ways and survived in countless others. The version of you reading this is, by definition, alive. You can only experience the branches where your consciousness continues. But from a God's eye view, from outside the branching structure, you're in a superposition of all possible states, living and dead, happy and sad, successful and struggling. Your lived experience is just one thread in a vast tapestry of possibilities, all equally real. The total number of parallel universes might be infinite. When we talk about the multiverse, it's easy to imagine a large but finite number of universes, billions or trillions scattered across some higher dimensional space. But the mathematics of many worlds and eternal inflation suggests something more extreme: infinity. In the many worlds view, every quantum event causes a split. Since quantum events happen constantly everywhere, the branching is continuous and ongoing. The number of branches grows exponentially, doubling and redoubling at an incomprehensible rate. Very quickly, the number becomes unimaginably large, and over time, infinite. Similarly, in eternal inflation, new bubble universes are constantly forming in the inflating space. The process never stops, having been going on for infinite time and continuing forever. The total number of bubbles is infinite, each containing its own history, its own galaxies, its own possibilities. Infinity is hard for human minds to grasp. It's not just very large, it's limitless, beyond counting, beyond comparison. In an infinite multiverse, every possible event happens, not just once, but infinitely many times. Every story is told, every life is lived, every variation is realized. You exist in infinite copies. But so does everything else. Infinity contains everything. Some parallel universes might be minutes ahead or behind ours. Time synchronization across parallel universes is a subtle issue. In quantum branching, all branches share the same timeline up to the moment of splitting. After that, they diverge and proceed forward independently. But what does forward mean across branches? If different branches have slightly different physical constants, time might flow at different rates. A second in one branch might correspond to slightly more or less than a second in another. Over cosmic timescales, these small differences could accumulate. Some parallel Earths might be minutes, hours, or even days ahead or behind ours in their local time. If you could somehow communicate with a parallel you might be talking to your own past or future self. Of course, we can't communicate across branches, so this remains purely theoretical. But it's a reminder that time, like everything else, might not be perfectly synchronized across the multiverse. Each universe ticks at its own pace, keeping its own time, following its own timeline through the landscape of possibility. Your now and the now of your parallel selves might not even align perfectly. You're all moving forward, but perhaps not in perfect step. Parallel universes might merge back together under certain conditions. Most models of the multiverse involve branching or separation, realities dividing from one another. But some speculative theories suggest that under certain rare conditions, universes might merge back together. In the many worlds interpretation, if two branches become sufficiently similar again, if their quantum states realign, they might interfere and recombine. This is called decoherence in reverse, and most physicists think it's extraordinarily unlikely for macroscopic systems. But at microscopic scales, it might happen. Quantum systems that briefly diverge can sometimes come back together, their different histories interfering to create new outcomes. This is the basis of quantum computing and quantum interference experiments. On cosmic scales, if two bubble universes in an inflating multiverse were to collide, they might merge, their laws of physics blending or competing at the boundary. The result would be a hybrid universe, stitched together from two different cosmic histories. These mergers would be violent, chaotic, and probably incompatible with life. But they represent a way that the multiverse might not just branch and diverge, but occasionally reconnect, creating feedback loops in the structure of reality itself. Separation might not be permanent. Even parallel worlds might find their way back to each other. You might remember events from parallel timelines. Memory is a physical process, encoded in the connections between neurons in your brain. But brains are quantum systems, subject to the same branching as everything else. Some researchers have speculated, very tentatively, that under certain circumstances, quantum effects in the brain might allow information to leak between nearby branches. Perhaps a memory from a parallel timeline could become weakly entangled with your brain state, creating a faint echo of an event that didn't happen in your branch. This would feel like a false memory or déjà vu, the sense that something happened even though it didn't, or that you've experienced a moment before when you couldn't have. Most false memories have simpler explanations, but if many worlds is correct and quantum effects matter in cognition, cross-branch memory leakage might be possible. It's highly speculative, bordering on fantasy. But it's a reminder that if consciousness involves quantum processes, and if reality is truly branching at the quantum level, then your mind might not be confined to a single branch as neatly as we assume. The boundaries might be blurrier than we think. Your memories might not all be your own. The multiverse might be a solution to the grandfather paradox. Time travel creates paradoxes. If you go back in time and prevent your own birth, how could you have existed to travel back in the first place? This is the classic grandfather paradox, and it's troubled physicists and storytellers for decades. But in a many worlds framework, the paradox dissolves. If you travel back in time, you don't arrive in your own past. You arrive in a parallel branch. When you change events, you're not rewriting your own history. You're creating a new branch where things happen differently. In your original branch, your grandfather survived, and you were born, and you built a time machine. In the new branch you've entered, your grandfather dies, and a different version of you is never born. But you, the time traveler, continue to exist because you came from a different branch. The paradox is resolved by the multiverse. Every possible timeline exists, and time travel simply lets you move between them. You can't change your own past, only create alternate versions of it. This doesn't prove time travel is possible, but it shows that many worlds makes it logically consistent. In a branching multiverse, you can visit other timelines without creating contradictions. The past isn't fixed, but your past is. Some universes might be made of exotic forms of matter. In our universe, ordinary matter is made of quarks and electrons. But string theory and other advanced physics frameworks suggest that other particles, other fields, other forms of matter might be possible. In some parallel universes, the fundamental building blocks might be entirely different. Instead of quarks, perhaps there are string-like filaments or higher dimensional brains. Instead of electrons, perhaps there are particles with completely different properties. These exotic matters might not form atoms as we know them. Chemistry would be different or absent entirely, but they might still organize into complex structures, perhaps even life, using principles alien to our experience. There might be universes made of dark matter analogues, or pure energy configurations, or quantum fields that never condense into particles at all. The variety could be limitless, constrained only by mathematical consistency. Our periodic table, our chemistry, our biology, all of it might be specific to this universe's particular configuration. In the broader multiverse, matter itself takes on meanings and forms we can't begin to imagine. We know one recipe for reality, but the cookbook might be infinite. Parallel universes might have different speeds of light. The speed of light, about 300,000 kilometers per second in our universe, feels fundamental. It's the cosmic speed limit, the rate at which information and causality propagate. But is it truly constant across all universes? In some multiverse scenarios, particularly those involving different vacuum states or compactified dimensions, the effective speed of light might vary. Some universes might have light that travels faster, others slower. This would have profound consequences. In a universe with faster light, causality would operate differently. Events could influence each other across greater distances. In a universe with slower light, the cosmos would feel smaller, more isolated, with distant regions forever cut off from each other. If light traveled infinitely fast, there would be no relativity, no time dilation, no horizon. If it traveled infinitely slowly, nothing could ever move or change. Most variations would be incompatible with structure or life. But somewhere in the multiverse's vast parameter space, there might be universes where light dawdles or races compared to ours, where the fundamental speed that governs reality is written in different units, leading to physics we could barely recognize. Even constants might not be constant everywhere. The many worlds interpretation means probability becomes personal. In ordinary quantum mechanics, when you measure a particle, there's a certain probability you'll get each outcome. These probabilities are objective features of the quantum state, written into the wave function itself. But in many worlds, all outcomes occur. So what do probabilities mean? If both results happen, why does the wave function predict one is more likely than the other? The answer is subtle. Probabilities in many worlds refer to self-location uncertainty. Before the measurement, you don't know which branch you'll end up experiencing. The quantum probabilities tell you how much of the wave function, how much of you, in a sense, flows into each branch. A 90% probability doesn't mean the outcome happens 9 times out of 10. It means that 90% of your future selves will experience that result, and 10% will experience the other. From your first-person perspective, before the split, you're uncertain which version you'll become. Probability becomes indexical, about your perspective within the multiverse, rather than about which outcome will occur. All outcomes occur, but you'll only experience one. And the quantum probabilities tell you how likely each experience is to be yours. It's a deeply strange way to think about probability, but it's how many worlds make sense of the Born rule. There might be universes where life is based on silicon instead of carbon. Carbon is the backbone of life on Earth, versatile in its bonding, stable across a range of temperatures, abundant in the cosmos. But carbon isn't the only possibility. Silicon sits just below carbon on the periodic table, sharing some similar bonding properties. In principle, silicon-based biochemistry is possible, though it will work differently than carbon-based life. In a parallel universe with different temperatures, different solvents, or different available elements, silicon might be the better choice. Life forms built from silicon chains might thrive in environments that would destroy carbon-based organisms, perhaps in colder worlds, or more reducing atmospheres. These silicon beings wouldn't be anything like us. Their biochemistry, metabolism, and evolution would follow different rules, but they might still be alive in a meaningful sense, self-replicating, adapting, becoming complex. The multiverse, if it contains enough variation, probably includes examples of every possible biochemistry. Carbon-based life like ours, silicon-based alternatives, and countless other solutions we haven't imagined. Life might be universal, but its implementation could vary infinitely. Your dreams might be glimpses of parallel worlds. Dreams are strange, filled with impossible physics, nonsensical narratives, and surreal imagery. We usually explain them as random neural firings, memory consolidation, or unconscious processing. But some have playfully speculated, what if dreams are glimpses into parallel branches? What if the quantum uncertainty in your sleeping brain allows weak connections to form with nearby worlds, letting fragments of their reality bleed into your experience? This is almost certainly not true. Dreams have much simpler explanations, and there's no evidence of cross-branch information transfer. But it's an evocative metaphor for the relationship between consciousness and the multiverse. Every dream is a kind of parallel world, a variation on reality that exists briefly in your mind. Some are close to waking life, others wildly divergent. And when you wake, all those dream worlds vanish, collapsing back into a single experienced reality. In a sense, your imagination already explores parallel possibilities. Dreams might not be windows to other universes, but they're windows to other ways things could be, other stories, other lives. The multiverse of your mind mirrors, perhaps, the multiverse of physics. Parallel universes might be the reason quantum mechanics seems random. Quantum randomness is mysterious. Why, when you measure a particle, do you get one specific outcome? Why that one and not another? The math gives probabilities, but the actual selection seems fundamentally random, built into nature. But in many worlds, there is no random selection. All outcomes occur. What seems random from your perspective is actually a deterministic branching into multiple realities. The apparent randomness is observer relative. Before the measurement, copies of you will experience all possible outcomes. You don't know which copy you'll be, so from your perspective, the outcome is unpredictable. But it's not that the universe randomly chose one result. It's that you're randomly one of the observers. This shifts randomness from being a feature of the external world to being a feature of subjective experience within a deterministic multiverse. The universe isn't rolling dice. You're just ignorant of which branch you inhabit. Whether this really explains quantum randomness or just relocates it remains debated. But it offers a vision where the universe's apparent indeterminism arises from our limited view, our confinement to a single branch of a fully determined multiverse. Behind the veil of chance, perfect order might reign. Some physicists think the multiverse is just advanced mathematics. Not everyone interprets parallel universes literally. Some physicists view them as useful mathematical structures, tools for making predictions and organizing theories, without necessarily existing as real physical places. In this view, the multiverse is part of our best mathematical description of reality. But that doesn't mean it's physically real, any more than the complex numbers, or Hilbert spaces, are physically real. They're part of the formalism, the language we use to capture the behavior of nature. This instrumentalist approach sidesteps metaphysical questions. It doesn't matter if other branches or bubble universes literally exist. What matters is whether the multiverse framework helps us make accurate predictions and understand experimental results. For some scientists, this is satisfying pragmatism. For others, it feels like dodging the question. If the mathematics works, why wouldn't we take it seriously as a description of reality? The debate mirrors older philosophical questions. Do mathematical objects exist independently, or are they human constructions? Does science discover reality or just build useful models? The multiverse forces us to confront these questions again. Are parallel worlds real or just math? And is there even a meaningful difference? You might be living in the rarest possible universe. While the mediocrity principle suggests we're probably typical, there's a counter-argument. Perhaps we should expect to find ourselves in a universe that maximizes observers, and if that configuration is rare, then we're actually in an unusual universe. If consciousness requires very specific conditions, fine-tuned parameters that occur in only a tiny fraction of possible universes, then most universes are empty, and the ones with observers are rare exceptions. In that case, every conscious being exists in an unusual universe by definition. The ability to wonder about your place in the cosmos means you're already in the rare subset of universes where such wondering is possible. This is the observational selection effect taken to its extreme. You can't be in a universe that doesn't produce observers, so the fact that you exist at all might mean you're in an improbable configuration. Rarity and typicality become relative. Among all possible universes, yours might be rare. But among universes with observers, it might be typical. The answer depends on the reference class you choose. Your universe might be both extraordinarily special and completely ordinary, depending on how you count. Parallel universes might explain the arrow of time. Time has a direction in our universe. Eggs break, but don't spontaneously unbreak. Heat flows from hot to cold, not the reverse. Entropy increases. We remember the past, but not the future. This asymmetry is called the arrow of time, but the fundamental laws of physics are mostly time-symmetric. The equations work equally well forward or backward. So where does the arrow come from? One answer involves the multiverse. Perhaps time's direction is a consequence of branching. As the universe splits into more and more branches, the total number of states increases. This increase might be related to entropy growth, giving time its direction. Alternatively, in an eternal multiverse, different regions might have arrows pointing in different directions. We live in a region where entropy increases in one particular direction, but elsewhere it might go the other way, or not have a clear direction at all. The arrow of time feels fundamental, but it might be a local feature, an accident of how our particular universe is structured. In the broader multiverse, time's flow might be more varied, less universal. Even the distinction between past and future might be contingent. There could be a universe where you're reading this from the future. If time flows differently across parallel universes, or if some branches are slightly ahead or behind in their development, there might be universes where you're experiencing this moment from what would be your future or past. Perhaps in one branch, you listen to this video tomorrow instead of today, but the alignment of events makes it the same moment from the universe's perspective. Or perhaps you listened yesterday, but quantum variations in timing shifted when this moment occurs relative to other events. This is deeply speculative, playing with the boundaries of causality and branching. But it suggests that the when of an event might not be absolute across branches, only relative within them. You think you're experiencing this now, but now might only be meaningful within your branch. From outside, from a view encompassing all branches, your different selves might be scattered across a range of times, all experiencing similar moments, but in slightly different sequences. Time, like everything else, fragments across the multiverse into countless local versions, each with its own flow, its own now. The multiverse might be shaped by an equation we haven't discovered yet. Despite all our theories and speculations, we don't have a complete understanding of the multiverse. If it exists, its full structure might be governed by principles we haven't yet uncovered. Perhaps there's a master equation, deeper than quantum mechanics or general relativity, that describes how universes form, branch, and relate to each other. This equation might explain why certain physical constants take the values they do, how many dimensions exist, and what the probability distribution across different types of universes looks like. Finding such an equation would be one of the greatest achievements in physics, a theory of everything that encompasses not just our universe, but all possible ones. It would let us predict what kinds of universes can exist, which are common, and perhaps even offer hints about our place in the larger structure. Until then, we're mapping the multiverse with incomplete tools, seeing glimpses but not the full picture. The mathematics that governs reality might be deeper than we've yet imagined. Somewhere in the space of possible equations, the truth waits to be discovered. Parallel universes might make death less final. Death, in our usual understanding, is the end of consciousness, the cessation of experience. But in a branching multiverse, the picture becomes more complicated. At every moment, quantum events in your body could go different ways. Your heart could beat or not. A neuron could fire or not. A blood vessel could clot or not. In most branches, these events resolve favorably, and you continue living. But in some branches, they don't. From your subjective perspective, you can only ever experience the branches where your consciousness continues. The branches where you die don't contain your experience by definition. So you might always find yourself on branches where you survive, no matter how improbable. This doesn't mean you're objectively immortal. In most branches, you'll eventually die as your survival becomes increasingly unlikely. But from the inside, you might experience an endless series of unlikely survivals, never experiencing your own death. It's quantum immortality again, a strange consequence of taking many worlds seriously. Whether it's true depends on subtle questions about personal identity and consciousness that we can't yet answer. But it offers a sliver of hope. In the infinite branching tree, some version of you might always persist, experiencing forever, never reaching an end. Some parallel universes might operate on different mathematical dimensions. We live in a universe with 3 spatial dimensions and 1 time dimension. But mathematics allows for universes with different dimensional structures, not just more or fewer dimensions, but dimensions that work fundamentally differently. There could be universes with multiple time dimensions, where causality branches not just from quantum events, but from multiple temporal directions. Beings in such a universe, if they could exist, would experience time in a radically alien way. Or universes with fractional dimensions, where space has a dimensionality between integers, creating geometries that are neither 2-dimensional nor 3-dimensional, but something in between. These mathematical possibilities might not correspond to physical realities. Many such universes would be unstable or incapable of supporting structure. But in the fullest possible multiverse, every mathematically consistent possibility might be realized somewhere. A comfortable 3+1 dimensional space-time might be one point in a vast space of possible geometries, each giving rise to its own kind of reality, its own physics, its own strange beauty. The shapes of space might be as varied as the shapes of snowflakes. The multiverse might mean that nothing is truly impossible. If the multiverse is infinite, or even just very large, then every event that's not explicitly forbidden by logic or mathematics happens somewhere. Every arrangement of atoms occurs. Every possible history plays out. Every story is told, every variation explored, every combination tried. This doesn't mean literally everything happens. Contradictions and logical impossibilities are still ruled out. You won't find a universe where circles are squares or where 2 + 2 = 5 in our arithmetic. But anything consistent with mathematics and logic occurs somewhere. In some branch, the most improbable coincidences align. In another, events we'd consider miracles occur through sheer chance. In yet another, alternate histories unfold where Rome never fell, or humanity never evolved, or the earth never formed. The multiverse becomes a library of all possible stories, and we're reading one volume among infinite shelves. Possibility and actuality merge. To be possible is to be real somewhere in the infinite expanse. Nothing is merely hypothetical. Everything is somewhere. And in the infinite branching of reality, you are a quiet miracle. As we come to the end of this journey through parallel worlds and cosmic possibilities, let's return to something simple and profound. You exist. In a multiverse of infinite variation, where every possible universe unfolds and every quantum event branches into new realities, your existence is both inevitable and miraculous. Inevitable because in an infinite multiverse, every possible pattern must occur. Miraculous because of all the patterns that could exist. You are this one, here, now, experiencing this moment. You are one thread in an infinite tapestry, one note in an eternal symphony, one story among countless others. You'll never meet your parallel selves or visit those other branches. You'll never see the universe from outside the branching structure. But you're part of it all the same, a participant in reality's endless flowering.